Okay, so you're typing in number 1. If you're borrowing one of my calculators, make sure as you type it in that everything looks right, because some of them are kind of old. Okay, then I'll come bring you a sucker. I want you to do what you can do from A, B, C, D. Those 4 parts. Okay, make sure you think about like units and stuff. I don't actually think you can do it from there. You can save like numbers if you saw under them. Do you want to touch your own? Or maybe a little a candy can. Okay, we're typing in our equation. What are you taking under? Oh, okay. Okay, so look at the units. And then guess, what are your units that you're... So, given that you have people per second and you want people. Is that a your thinking? Okay, make sure you read through the paragraph. There are 2 equations or 2 rates.
But is that really an equation?
It's not really an equation, it's a constant, but it's still people per hour. Is that one? Thank you for your note. That is correct. Okay, so then part B, how many people are in line? So what do you need to take into account? Yep, they're already in line. How many people got in line? And then there are also people getting out of line. So you need to figure out how many people got out. It says they're getting off at 0.7 people per second. So you have to take that rate, and then you can either integrate it or you can just think about it. If it's 0.7 people per second times how many seconds, then you could figure out that rate too. So integrating to 300, yes ma'am, correct. Yes. You need to set the integral on your paper. It doesn't matter, you gotta set it up. You can calculate it in the calculator, you still need to write it down. Okay, it's because this, because you already have this giant bracket. So we need to just part B, who's already in line? Okay, 20 plus, how many people got in line? You put it equals there. So plus 270, how many people are getting off though, it says. So if there's 300 seconds, 0.7 people per second. Or you can do an integral or reduce units. So do your initial people first, so 20 plus, how many people got in?
It's like sort of like a brain.
Kind of, yeah. Except you have like 2 integrals instead of only 1. Uh-huh. So this is them trying to help you out. What happens if 300 people stop getting out? Now, are they still getting out of line? Yes. So they're reminding you that after 300, nobody else is getting out of this. So that's kind of like them trying to give you a hint for that. You would minus the integral. Okay, so you have 2 ways to do it. You can set it up as an integral, 0 to 300 out equals 7. Or you can just think about it as 0.7 people per second times 300 seconds.
Yeah.
So it's up to you. You can do it either way. Yeah.
Okay, so let's check your answer now. Just to give you a heads up, since I didn't know how much of this we'd finish, I put all the answer keys at the back. So your packet looks like it's like 8 pages. The last 4 pages are just pictures of the answer key in case we don't get to something. Or if you want to work ahead, then you're welcome to do that. Okay, so part A, we have people per second. I would write those units down. And what are these people doing? They're getting on the escalator. So I'm going to count that as my in equation. Now, what else is happening at the same time? Some people are getting on, some people are getting off the escalator, right? So I'm going to write over here to the side my out equation. I'm going to call it E of t for exiting, just because I don't know what else to call it. Okay, and it says it's 0.7. Okay, now you didn't have to do that, but just for me, I have people going in, people going out. They're both people per second. That's good. Okay, part A, how many people enter the line? What do I do? Integrate, very good. From when to when? 0 to 300. And then which function? R of t dt. Okay, then if you type that into the calculator here, math 9, 0 to 300. Okay, then alpha trace y1 dx. You get 270 people. 270 people. Now, what was your hint there? Okay, your function was in people per second. You want people. That's an integral. Okay, part B. Says during 0 to 300, there are always people in line. How many people are in line at 300? Okay, what do I have to take into account? Okay, the in, the out, and what else? There were already 20 in line. If you read carefully, right here it says, at time 0, there are already 20 people in line. So I would do 20 plus. Now, you have 2 choices. You can set up the integral again, but we already know how many people it is. How many people got in line? 270 minus. There are 2 ways for you to do this second part. If it's 0.7 people per second, you have 2 ways you could have set that up. I'm going to set it up as an integral, but could you also just multiply 300 by 0.7? Sure. It doesn't matter whichever way you want to do it. If it's 0.7 people per second for 300 seconds, you can just multiply, but I want to show you it comes out the same. Math 9, 0 to 300, 0.7 dx. Okay, gives me 210. Or I can do 0.7 times 300, and you still get 210. So it doesn't matter which way you set that up, you'd be minusing 210 people. Hello?
Kelly is not in my room. She might be taking the AP Bio though. It's in the double gym. They are. And they start at 8, so most of them are about 4 hours. So she should be getting out around noon. Some of them are 5 hours though, because they count it right in the middle. Okay. If you send me an email, I have her on Remind 101. I can send her a message, but okay. 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 Yeah. Sorry. Bye. Thank you. Okay, we'll have to do it in class. But after we do notes and stuff, then I'll look at it with you, okay? Not this class, but tomorrow. This class is fine. Just this is the day before their AP test. Okay. So I have 20 plus 270. That's 290. Then I need to minus 210 off. How many people are in line? 80. Good. 80 people. Okay, part C. What is the first time that there are no people in line for the escalator? Now notice, it already said from 0 to 300, look right here, there are always people in line. So I'm not worried about a number before 300 giving me 0. Okay, think about for part C, what do I need to take into account for there to be nobody left in line? I already have how many? 80. And then when you look at your equation here, what happens at 300 to your people per hour? It goes to what? 0. That means that after 300 seconds, nobody else is getting on the escalator. So what's the only rate that I have to worry about? The people getting out of line, right? Now, what do I do at that rate? Do I add it or subtract it? Subtract it. And then I'd go 0 to 300, but instead I'd make that 300 to T. My 0.7 goes here. And then equals 0. Very good. So I want you to think about, these are the people already in line, because I already found this in part B, right? At 300 seconds, I already have 80 people. So if I keep integrating from 300 until whatever this time is that I don't know, I want to have 0 people left over. Yes, ma'am? There is. You could just make this a 0.7 times T, which we're going to end up finding. I'm just doing it the way I would have thought to do it, but that would have also worked. Okay, so from here, my integral is negative. I'm going to bump it across to the other side. So I have 80 equals 300 to T of 0.7 dt. Now, this is where I'm going to show you why just multiplying the rate is the same. What is the integral of 0.7? What would it be? 0.7. I'm going to use an x just to change the letter, but then what would I do with my top and my bottom? I would just plug it in, right? So when I plug in that, I get 0.7t. What do I get on bottom when I do 0.7 times 300? 210. And then what do I do with these two guys? Subtract. So I'd have 0.7t minus 210. And then from there, what do we do to solve? Add the 210 across, divide by 0.7. Okay? Yes?
How come when you're doing the interview, you set it up to 0.7? Why don't you set it to 0.7 minutes?
Because there's not an x in it. It says 0.7 people per second. That's already the rate. Now, when I do the antiderivative, that's where the x comes in. Yeah? Then you plug in your endpoints and you subtract. Now we're just going to keep solving. So I'm going to add my 210 across. 280 plus 210 is 290. And if that equals 0.7t, then I have to divide by 0.7. 290 divided by 0.7 gives me 414.2857 seconds. Now, they told me that it had to be after 300 seconds. So does that answer look good? Yes. Now, the other way, if you look at the answer key, the way that they set it up, they skipped this whole first line. And they basically just said, okay, if there's 80 people in line, how many have to get out of line? 80. So they just set up this integral needs to equal 80. That would have been fine too. Because you're thinking about, there's 80 people in line, I want there to be nobody in line. 80 people need to get off. Either way works. Okay? Alright, part D. Part D says, for 0 to 300, at what time is the number of people a minimum? To the nearest whole number, find the number of people at this time. Okay, we've done a bunch of these. What do you need to do with the in and the out graphs? You need to find where they what? Where they intersect. Very good. So for part D, go into your calculator. Go into y equals. I already have my in graph typed in. I want you to type in your out graph. So they're coming in at this long complicated thing you already typed in, but they're going out at 0.7. Now the next thing that I need to do is adjust my window. What is the x for my window going to be? 0 to 300. And then for my y's, I'm going to look in my table and just kind of spy on where my numbers are at. So these are all decimals. They all look to be pretty small decimals. So in my window, I'm going to go 0 to 300. And I'm going to make my y's maybe like -3 to 3. Just to zoom my graph in a little bit so that I can see the graph better. Okay? So 0 to 300, and then I look in my table to try to pinpoint where I want to put my y's. Okay? So let's look at the graph. Okay, there it is. This is my in graph. Okay, there's my out graph. Okay, so let's sketch a graph here real quick. So it goes up, down, and then this one is flat. Okay, this is my in, this is my out. Which critical number, I'm going to give you a couple seconds to think about it. Which critical number will be a minimum? Think about that for a second. Okay, I have two intersections. I need to figure out which one is a minimum and which one is a maximum. Okay, for the first chunk of the graph, from here to here, which rate is bigger, the in or the out? For this first chunk. The out. That means overall what's happening to the line? It's decreasing. So I'm going to put from here to here, line is decreasing. Okay, now what about the next section of the graph? From here to here. What's happening to the line? There's more coming in than are going out, so what's happening to the line? The line is increasing. Okay, then for my last little chunk, here to here, what's happening to the line? The out function is bigger, so what's happening to the line? It's decreasing again. Okay, now that you know the signs, it goes decreasing, increasing, decreasing. Which one is a minimum that I care about? The first one. So find it in your calculator. Second, trace 5. And I'm going to write, I have a relative minimum at t equals, and I think it's like 33 maybe. 33.0132. Okay, then I'll put because the rate of people in line changes from negative to positive. Okay, now question. Just because it changes sign doesn't make it the winner. It's only the winner if there are no other critical numbers. So, did they cross at any other points on my window? Yes, that means we can't assume it's the winner. We have to make a what? Candidates chart. Very good. So, I'm going to set my chart up down here. What else has to go in my chart? So, I have my 33. What other two numbers? Good. 0 and 300. Now, the good news is that we already know the other two values. How many people were in line at 0? They already gave you that. 20. And how many people are in line at 300? We already found that. Part B. There were 80 people in line. So really, the only value that I have to find is the value at that 33. I already knew the other two from the other parts of the question. So let's do it. Second quit, I had 20 people in line plus. I need to integrate my y1 from 0, oops, that's not the right button. Math 9, I need to go from 0 to 33.0132 of y1 dx, and then I need to minus the integral 0 to 33.0132 of my y2. And remember, my y2 is just that 0.7. So I'm saying there were 20 people in line, plus how many went in, minus how many went out. Okay, at that time, there are 3.8 people in line, which is obviously going to have to be rounded. Now, what is my minimum value now that I have my 3 candidates? The minimum is 4 people at 33. Yeah? Okay? So I'm going to write that just over here. So the minimum people, or minimum value, is 4 people. I'm plugging in the intersection to the version B. Because remember, I want to know how many people are in line. So I need to do 20, look, you can see it right here, 20 plus the integral that was going in, and then minus, if you look up, the integral that was going out. So that's why the minus of 0.7 is here. Okay? At 33.0132, and that would be seconds. Okay? Oh, I should have just, don't box anything. Okay? What's wrong with my chart that it's not going to give me full points? This is the number of people. So if you don't have a function name, just put what it is. So on this side I have time, this I have the number of people, and then that'll be good. Okay? Yes, ma'am. Because it was a max. And so if I know I'm looking for an absolute min, I know the max isn't going to be the winner. You can put it into the table if you want to, but you just know it's not going to be the smallest value if it's a maximum. So this one here was a min, that's why it made the table. But since I was looking for the absolute minimum, I did not choose the max. Make sense? Huh? So on the left side, my out rate was bigger than my in rate. So overall, the line was going down at that point because people were getting out of line faster than they were getting into line. Okay, then on this side, they're getting in line at a faster rate than they're going out. So overall, what was happening to the line if you kind of put them together? The line would have been increasing on that section. So if my line changes from decreasing overall to increasing overall, that's a minimum. But you're kind of putting the two rates together to see what their sign would be. Okay? All right, there's one more calculator question that we're going to do, and it's this one. Okay, so I'm going to give you a couple minutes to try it. A, B, C, D. Okay, you have water going into the tank at an equation, and then you have water going out of the tank at an R of T. So work through those guys. A, B, C, D.
Is that the next one?
We're doing the next calculator question. And then everything after that are answers.
Okay, what are you doing in part A? Okay, now I can't take the derivative because they want r prime and I don't have an equation for r. What can I do instead? Average rate of change.
Oh.
See what I mean? If they were asking for w prime, you'd take the derivative.
Okay, so for part A, if you want r prime, that's a slope, but I don't have an equation. That means that, and also notice it says estimate. That means you're doing A rock. Now, what A rock should I do if I want r prime at 2? 1 to 3, very good. I want A rock from 1 to 3. So, for part A, I would have put r of 3 minus r of 1 over 3 minus 1. R of 3 was 950. Minus R of 1 was 1190 over 2. Now notice it says indicate units of measure. So if R is in liters per hour, what will R prime be in? Good. Liters per hour squared. Now I want you to think about overall this rate is going to come out negative, right? So what does that tell me about the liters per hour? That it's decreasing, right? And you can see from these values in the chart that they're going down each time. Okay, part B. Using a left Riemann sum with the 4 subintervals in the table, estimate the total amount of water removed from the tank. So for part B, I know I'm doing an integral because this is liters per hour and I want to know the number of liters removed. So I'll go 0 to 8, R of t. And then remember that since it's an approximation, I'm going to put a squiggly equals. I don't think you'd lose points for that. Okay, but remember, Riemann sums aren't exactly equal, they're an approximation. Okay, Riemann sum, I'm doing a left side from 0 to 1. What's my delta x? 1, what's my left y value? 1340, very good. Plus, from 1 to 3, what's my delta x? 2, what's my left y value? 1190. From 3 to 6, what's my y value? 3, what's my left y value? 950, right? And then from 6 to 8, my width is 2, and my left y value is 740. Just depends. Do you remember how you tell the difference? If your delta x is the same, you can GCF it to the front. If not, you have to do each one. Okay, then it says, is this an over or an underestimate? Give a reason for your answer. How do you tell if a Riemann sum is too big or too small? Concave is for trapezoids. Good. Look at your y values. What's happening to them? They're decreasing. And I did a left side, so I would just sketch it. If I do a left side Riemann sum, how does it fall? It's an overestimate. Very good. So I would say Riemann sum is over actual value because R is decreasing. So the left y value is the greatest on each subinterval. Riemann sum is over the actual value because since R is decreasing, the left y value is the greatest on each subinterval. So that tells me my estimate is over. Okay? Alright, part C. Use your answer from part B to find an estimate of the total amount of water in the tank at the end of 8 hours. Okay, first thing that I would do is look back at the question. How much water is starting in the tank? Sometimes it starts empty, but sometimes it doesn't. Okay, very good. If you look right here, it says at time 0, there's already 50,000 liters of water. So if I want to know how much water I need to do 50,000 plus, then which of my rates is going in? My R of T or my W of T? Very good. Look right here. This is my out, but I also have an in. And notice, one of them is a chart, but then one of them they gave you an equation. So I have out for removal, but I have pumped in for my equation. So you would have had to set up the integral from 0 to 8 of our W of T dt, and then minus 0 to 8 of R of T dt. So I'd be adding what's going in, I'd be minusing what's going out. Now, if I have the equation for W, where are you going to do that? In your calculator? Okay, do it, and then what's the answer for this one going to be? We already know it. We did it in part B. So I have 50,000 plus math 9, 0 to 8 of alpha trace y1 dx. And then I need to minus the answer from part B, which I actually never typed in, so I'm going to have to do that now. So I'd have to type in 1340 plus 2 times 1190 plus 3 times 950. And then plus 2 times 740. And usually if it's not a short version, then they'll at least make it not that many. So then I need to do this minus 8050. So the total amount of water in the tank at that point would be about 49,786 cubic liters, or liters.
That's like the last equation where we added the initial to the in and it's from the
Yep.
out.
And then in this case, your out, though, was just a Riemann sum. So you would have had to write it out and figure out what it is in the calculator to do it. So I had 50,000 plus. My integral came out to be, I'm going to come back up here and put 8050. So it'd be a total of 49,786.1953 liters. Okay? Yeah. No, you could have just figured it out. So if you had put 50,000 plus the integral and then put minus 8050, that would have been totally fine. If you had already found this value, then you could substitute that value here instead of setting up the integral. Okay? All right, last part, part D, 0 to 8. Is there a time when the rate that the water was pumped in is the same as the rate that water was removed? Explain why or why not. Okay, this is what I'm going to do. Okay, I'm going to set up a time function for my R of T, and I'm going to set up one for my WT. Now notice, R, they already gave me the values, right? So they told me 0, 1340, 1, 1190, 3, 950, and then 6, 740, and then 8, 700. Now, you already have W in your calculator. So I want you to go into your table and find the values at 0 and at 8. At 0, what is W of T? Yeah, I'm getting to it. It was, I got 2,000. Oh, okay. And then at 5, what is it? 573.0095. Okay, I want you to think about, at 0, which rate is greater? W is greater, right? But at 8, which rate is greater? R, right? So think about, if this one started off bigger and that one ended bigger, did they have to cross at some point? Then did they have to be equal? Yeah. So that's what I would do, is I would just say at the beginning, at 0, W is greater, but at the end, R was greater. So that means that they must have been equal if they intersected. Now, what theorem says that? IVT, because both functions are what? Continuous. And if you look up here, it tells you they're differentiable. If they're differentiable, are they also continuous? Yes, yes ma'am.
On mine, for 5 it says that, but for 8 it says 81.5.
Oh crap, I looked at 5. I should have looked at 8. I was looking at totally the wrong time. You're right. So sorry. Let's fix it. Okay, this was 81.5244. I don't know why I was looking at 5. Okay, so fix your chart. And now let's explain what we just said. So, do they have to be equal? Yes. IVT guarantees this because both functions are continuous. And W of 0 was greater than R of 0, but W of 8 is less than R of 8. So they must have intersected somewhere on that interval. Something like that. Okay, it doesn't have to be super official. You'd basically just be stating that if one of them started off bigger, the other one ended up bigger, then they had to cross. And then you don't even have to find the value, I don't think. It just says explain. Okay? And then if you labeled your tables here, then you don't have to restate those values in your explanation. Okay? All right. We have time maybe for not really much. So,
Pretty good session.
yeah, good. Woo.
Let's wrap it up.
Wrap it up. Okay, so don't stay up all night cramming on stupid crap. Get sleep so that your brain works tomorrow. Find a friend, call them in the morning, make sure they're awake, and y'all are going to do great tomorrow. You know